Okay, so the question now is, if you don't have constant volume work or constant pressure work, what if you have that they're both changing at the same time? This is going to be called polytropic work. Okay, so let's talk about polytropic work. Polytropic work. Polytropic or polytropic work. I say polytropic. And I want you to understand that polytropic work is a special case. It's what our first model of this class. We're going to model things as polytropic work. So here's what's going to happen. If we go and we have a pressure volume diagram, and let's look at our piston cylinder. We might look at the piston cylinder as it's moving and we say, oh, let's take a pressure measurement and see what the corresponding volume is, and we make a pressure measurement there. And we might take another pressure measurement there, another pressure there. As we're going through a process, this might be the data points that we have. Okay, those are the data points. Now, what polytropic work does is it's a model that does a best fit line. So what we're going to do is try to fit a line, a best fit line through all of this data that represents what the boundary work looks like. Okay, this is going to be our polytropic fit line. It is not what's actually occurring. It is a good model. In fact, I probably exaggerated my points there. It's a pretty good model to what's actually happening there. How we do that, polytropic work, is we say PV to the N is equal to constant. This is a power series. Is a power fit to the equation. PV to the N is constant. And there was going to be an alternative assignment that I'm going to release today that will have you explore. This is the polytropic exponent. And that exponent, N, determines the shape of the curve. Okay, determines the shape of the curve. Now, N is equal to 1 does not mean it's a straight line. Let me say that once again. N is equal to 1 does not indicate that your graph is a straight line. The alternative assignment is for you to figure out what polytropic exponent does indicate that it's a straight line. You're going to explore that and try to figure out what's going on. Okay, so if I were to look at different things here, what we have here, PV, we have looked at two situations already. First one is this. What is that line I've just drawn? Well, that's pressure is equal to constant. Okay. Area under that curve is very easy. It's just a square. We have volume is equal to constant. Here, this is volume is equal to constant. Area under that line? Nothing. There's no area under that line. But then we have these other things that can occur over here. Maybe this is N is equal to 2 and N is equal to 1. We have all these curves that happen. And then the shape of the curve determined by the polytropic exponent, and it's a best fit line. Okay, it's a best fit line. It's a model that we're following here. Now here's the thing that I want to let you know. In a problem that was given to you as a homework assignment or in an exam, I have to say that this problem is polytropic. I have to say, the mode of the expansion and contraction, model it as polytropic. I'm either going to tell you to model it as polytropic, or the alternative, what I'll do is I'll say, here's some data points. I want you to tell me what's going on. And if you graph those data points and you find out that it's a straight line, then you can say, hey, it's constant pressure. If you say it's straight, it's constant volume. Okay, but otherwise it might have a different levels of different curves that are happening there, and I'm going to maybe want you to find out, okay, tell me what the exponent N is. How can we find that exponent? But the key thing here, what I'm trying to say is that in the absence of any information, you are going to assume that you have a constant pressure process. If the problem statement does not say anything, it's a constant pressure process. If they say the piston expands or contracts, assume constant pressure. However, if the problem statement says this is going to expand polystropically, or it's going to expand with PV to the N, then and only then can you make the problem be polytropic. And I say this and I emphasize this and I've belabored this point because I've seen so many students over and over again make all problems polytropic. They've tried to take a problem that is constant pressure and make it polytropic. They made an assumption that is not true. So again, you need to read the problem statement and get information and only then can you say that the problem is polytropic. Okay? So let's look at these. Let's look at this again. Let's look at PV to the N, and let's look at the cases. The cases for N. Okay. If N is equal to 0, I should say PV equals N is equal to constant is actually how this is looking. PV to the N is equal to constant is a polytropic process. If N is equal to 0, what is that case? Well, that case, if V to the 0 is 1, so you have P is equal to constant. This is equal to the constant pressure. Okay, we've already talked about that. So you could say that constant pressure is a special case of a polytropic process when the polytropic exponent is equal to 0. But we just don't do that. We just don't do that. There is some other cases. N is equal to 1. Okay, and then N is not equal to 0 or 1. So it is everything else. Everything else. Okay. So we want to look at these two cases now. We want to look at N is equal to 1 and N is equal to everything else. And we're going to create an equation for this. Ooh, boring myself today. All right, let's look at N is equal to 1. If N is equal to 1, okay, we're going to have PV to the 1 is equal to constant. But we don't write things like that. You don't write things PV to the 1. You just write that as PV is equal to constant because anything raised to the 1 power is itself. Okay, so that's what we're talking about. So what does this mean? This means that P1V1 is equal to P2V2 is equal to P3V3 is equal to P4V4 is equal to blah, 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 blah. We're saying that if we take any pressure volume pair and multiply it together, we are going to get a constant value, okay? Any pressure volume pair. Now we can't take P1V2 or P3V1 and do that, but at any state, if you take a pressure and volume, it's going to come together at the constant, it's going to be a constant value. So let's see how we would evaluate the work. Work is equal to the integral of PdV. Okay, boundary work is equal to integral of PdV. And we're going to evaluate this between 1 and 2. Now we can't take pressure outside of the integral because it's not constant. And so what we're going to do is substitute. And what we're going to do is for pressure, what I'm going to substitute in is I'm going to substitute in constant over V. So 1 to 2. For pressure, I'm going to solve this equation here, and I'm going to solve it for pressure, which is going to be constant over V dV. Okay. Now what do I have? I have a constant. I can take that out of the integral. So this is going to equal to constant times the integral from 1 to 2 of dV all over V. Now this is an integral I can do, and you've probably seen this before. What is this integral? I'm waiting. You're shouting it at your computer screen. It's natural log. Natural log of V. So you need to know your rules for natural logs. Those are going to be helpful in your homework tonight as you're trying to solve. One of the things that you're going to do is use natural logs to help you solve for the polytropic exponent. And we're evaluating between V1 and V2. Okay, so what would this be here? This is going to be constant times, with my evaluation, I'm going to go natural log of V2 minus natural log of V1. Okay, now we know from our rules of logs that we can write when something is subtracted from each other, when two logs are subtracted, we could write this as constant times the natural log of V2 over V1. All right. Now, I don't really like this equation because it has constant. I don't know what constant is, but I recognize that constant is equal to PV. Which PV? Well, it could be equal to P1 V1, natural log of V2 all over V1, or it could be P2 V2, natural log of V2 all over V1. Either of those could work because P1 V1 is equal to constant and P2 V2 is equal to constant. We could put those in. You don't have to remember this because this is on your equation sheet. I give this to you every time when n is equal to 1. Every time n is equal to 1, you will get this equation. P1 V1 natural log of V2 over V1 or P2 V2 natural log of V2 over V1. Now, you don't have to do, this does not have to be, remember how we do the integral. This is our starting state and this is our ending state. 1 is starting, 2 is ending. I could do between 1 and 4. What would I do if I got between 1 and 4? My final equation would be P1 V1 natural log of V4 over V1. That's going to give me the final minus the initial. I could do P2 V2 natural log of V1 V4 over V1 or P3 V3 natural log of V4 over V1. Because again, all those pressures in between 1 and 4 times their corresponding volume will give me the same constant. But remember, state 1 is where we begin and state 2 is where I want to end calculating my work. I need you to understand this equation, not just use it. I want you to understand where this equation comes from, how it's made, how it's used. Because again, this is where you can plug and chug, absolutely, and get the right answer, or you can actually try to understand this and help. You're going to do better on the homework and on the exams. Remember, this is always the case. It's on your equation sheet. Don't have to do the integral. I would encourage you to do it once or twice, but after that, you're done. Memorize it. Look at the equation sheet, whatever. All right. Now let's look at the other case. What if n does not equal 0 or 1? It's everything else. Okay, so here we're going to have P1 V1 to some value n is equal to P2 V2 to some value n is equal to P3 V3 to some value n, and that's equal to constant. We can keep going here. P4 V4 to the n, P5 V5 to the n. Okay, PV to the n is equal to constant is what we're looking at here. This is what we're going to be saying. And so we need to do the integral. Work is equal to integral. I'm going to just go between 1 and 2 of PDV as we started before. Again, I want to get rid of the pressure. So what happens here is I solve for pressure here, and I'm going to get, this is equal integral from 1 to 2 of constant all over v to the n times dv. This is a little bit different than what we had before, but I can still take constant out of here, and now I have the integral from 1 to 2 of dv all over v to the n. Okay, now I don't like to have my things with exponents in the denominator when I'm doing integrals, and so I'm going to bring it to the numerator and say this is equal to constant 1 to 2 of v to the minus n dv. And we have to integrate that bad boy. Now, the way I think about integration and the way, what is integration? It's the opposite of a derivative. And so when I wrote this out here, and maybe you can do it easier, but I wrote that this is equal to v to the 1 minus n all over 1 minus n. And I can check to see if that's right. Evaluate it between state 1 and state 2, because if I take the derivative here, v to the 1 minus n is going to come out. It's going to cancel with the denominator. Then I'm going to subtract 1 from the exponent, and that's going to give me minus n. And that's exactly what I had in the integral, so I'm good. I'm good to go. I'm good to go. I've done it. I've successfully integrated this. All right, so what's this going to show me? It's going to say constant times, well, I'm going to evaluate this as it's going to be v2 to the 1 minus n minus v1 to the 1 minus n all over 1 minus n. All right? And here's where we do something clever. Here's where we do something clever. Because we know here we have to multiply this by constant. Constant is multiplied by this whole equation here. Well, what do I choose as my constant? Do I choose P1 V1 to the n, or do I choose P2 V2 to the n? And the trick is, we do both. When we're multiplying by V2, we use P2 V2 to the n. When we have V1, we use P1 V1 to the n, and that gives us this equation. P2 V2 to the n, to the v to the 1 minus n, minus P1 V1 to the n, times v to the 1 minus n, all over 1 minus n. That's what we have. Now there's some simplification that we can make there, and it's quite convenient. P2 is n 1 minus n. Remember, we add these exponents together, and we're just going to get P2 V2 minus P1 V1 all over 1 minus n. Again, this is the initial and the final point. So we could go between P3 or P2 or whatever we want to work with. But this is the equation for work for any polytropic process when n does not equal 0 or 1. It's always going to be the case. Always going to be the case. Don't have to remember it. Just use it. Just use it. Okay? This is important. That's the other thing I want you to know about this is when you're in the English system, you got to work about conversion. You always, it's not just plug and chug. You have to worry about conversions. Even when you're doing with SI here, you got to worry about conversion because work is in kilojoules. You want your answer to be in kilojoules. If I give you something in bars, you're going to have to convert that to kilopascals. If I give you pressure in PSI and my volume in feet, you're going to have to do some conversions here. So don't just plug and chug. Understand the conversions are also part of it. Okay. Your homework tonight is going to be dealing with polytropic processes. You're going to have to understand this. One of your problems has multiple processes that you're going to have to work with things. It's kind of like a we'll talk about it later. Let's talk about how we have to fill in the missing points here. But know that these two modes of polytropic work. We'll stop there for right now.